Thank you very much. So, I will explain some things today and I love board and chalk. So, this is a field we worked for a very long time and it encompasses areas, even very last part will be little bit of biology. But this is a new view. I do not have a slide, but one thing that I should let you talk little bit about, that see, as scientists we usually learn from nature and we try to explain phenomena, and then whether they are in the laboratory or maybe happening initial period, they are mostly in the nature, but now increasingly we are explaining things we observe. And the important things that what get people excited, if you have last 15-20 years, there are two kinds of research that makes people really excited. One is like the phenomena which is high temperature, say superconductivity or many other similar phenomena that came in the last giant magnetic resistance, and many things that came out, and other things is the technology, and with an experimental made tremendous amount of progress, because I have gone through, I have seen all the microscopes, electron scanning, tunneling probe, all the microscopes were actually last 10, 15, 20 years. Fairly, I have a talk which is I give to KVPY, which is for undergraduate students, which actually chronicles the history of two things. One is a microscope, another is a spectroscopy. So, microscopy and spectroscopy together. In theoretical chemistry also we have, or in theoretical physics, we have two very distinct branches, though they do get combined, but they are distinct at the very basic. One is the quantum mechanics and quantum chemistry, and the statistical mechanics or statistical physics. Okay. And there are many cases, they are both, you need both, like you want to understand Raman scattering, because that is a diagnostic tool, or you want to understand some conductivity, then you need both quantum and classical, quantum and statistical mechanics. Statistical mechanics based on some principles, quantum mechanics you know based on essentially Schrodinger equation. Now, these are both microscopic approaches. That means, in both the two cases we start with atoms and molecules. In quantum mechanics we have an electron, say, and or in correlated system few electrons. In statistical mechanics we start, which is essentially example is thermodynamics, we call it large amplitude systems or big systems, Avogadro number of particles, very large number of particles. The phenomena that we try to explain are like phase transition or polymer properties or certain say structure of surface layers are based on interactions between atoms and molecules. But the phenomena that is our basis, and interactions come from quantum. But when you want to explain the large amplitude phenomena, then there is a certain cooperativity that comes. So, that is what we do in statistical mechanics, and the new thing that kind of come into from essentially from mid-80s. So, it is about now 30 years old. There is a new paradigm that has been developed, which give you an intermediate level. That means, it is not in the molecular level completely, and then also not in the thermodynamic level. So, at the thermodynamics level you observe things, but the molecular details are washed out. You do not care when you say what density of water is 1 or specific heat is 1, you do not care about what is the structure of molecules or what are the interactions. Okay. Then we know water undergoes melting at 0 degree centigrade, evaporation at 100 degree centigrade, and then all the other kind of transformational properties, many of them now routinely used in nanosynthesis, and I will go through that little bit, where the microscopic details sometimes gives you information which does not translate into observable properties. So, it is a big task to start from atoms and molecules and intermolecular interactions and take it all the way to predict that ice melts at 0 degree centigrade. However, there is an intermediate level description which is the energy landscape, which started long time ago, but it's now become very popular for reasons you will see. So, what is an energy landscape? Sorry, why? As I said, it's an elegant description of collective phenomena, a macroscopic phenomena like phase transition, protein folding, glassy dynamics, many things, where if you try to explain these things at the level of single particle, then that does not work. You cannot explain why ice melts. You take an example that you take snapshots of a same crystal near melting, look at a single particle properties, you will not be able to differentiate between them. Yes, you look at the diffusion constant for a long time, you would be able to say, but in a structural aspect there is no difference. So, this is the basic motivation. I will give more motivation as I go on. So, the basic thing, that idea goes back to Landau theory, which I will describe little bit. As I said, little bit of an element of class will be here today. Then the barrier crossing rates, the kind of things that Rajorshi does and many physical chemists do. Then we will go to one textbook anomaly in a Brownian mixture. Then there is spinel decomposition and the material science things, and phase transition in liquid crystals. Then this is something which is has become popular of late, nucleation and Ostwald's step rule, in a nanomaterial synthesis like zeolite or phosphates, all these things you need invoke that. Then I will have little bit of you will see actually, you will see as I progress through this, you will see the increase of sophistication. And so this was something we started in say about 2000 or 2004-05, and this is something we just did this year. So, origin of energy landscape in the language started with Johari and Goldstein in a important paper. They were trying to understand glass transition, and what they are finding in glass transition an interesting behavior. This is something happened at very low temperature, and this is something huge number of physicists and physical chemists are interested. That I take a liquid, you can take chlorobenzene is a good example, neopentanol, another good example, and you almost in any of these molecular liquids, and you cool it, then you find if you can avoid the crystallization, viscosity suddenly increases very fast, and all the relaxations become highly non-exponential. However, when you go deeply supercooled liquid, then again a transition takes place from non-exponential, it becomes like exponential, very funny, and then markedly non-Arrhenius to become Arrhenius temperature dependence. I will plot a few and I will show you photographs of that. In order to explain, they first time said that what happened, the energy landscape of the system, actually energy landscape of the system does not change, but something else changes, that means the way we explore the energy landscape, that changes dramatically, and that is the first time people start talking of the energy landscape in order to explain this complex situation. Now, let me tell you why it is difficult. When we are talking of the relaxation, we are talking sometimes of 10 orders of magnitude of time, okay, or talking of viscosity that goes from something like a centipoise, so 10 to the power 10 poise. 1 centipoise is 0.01 poise. So, you are talking of 12 orders of magnitude, huge magnitude. This much of the things we do not do in the laboratory, but this has been, as I told you, hugely important area in physics and chemistry for a very long time, and people are still now trying to understand these phenomena. Okay. Now, as around that time 1980s, there is a lot of development took place in a model called Ising model. Ising model are the models you know probably, they are spins and they are interacting with nearest neighbor spins. Spins can only have two directions, up and down. If they are parallel, they like that configuration, that is called ferromagnetic interaction, and if they are anti-parallel, they do not like that, that is called anti-ferromagnetic interaction. Okay. Now, this undergoes in a 2D and 3D undergoes phase transitions in Ising model without random. However, if I make the interaction between the two spins is a random. So this typical interaction potential is given like that. So H nearest neighbor interaction sigma I can be 1 and minus 1. So if there are both like that 1 1, then it is minus j, but it is 1 another one minus 1, then it becomes plus. That antiferrometric interaction. What these people, starting with the guy Sherrington and Kirkpatrick, very famous people. Many of you have not, you are not first time you are hearing this, but these are very, I don't know, I cannot have the superlatives actually, how important these things are. You may not have nearest neighbor, you might have nearest neighbor. This thing becomes the random. And Sherrington-Kirkpatrick model, we say, I am not going to do too much of that. This j square undergoes a Gaussian distribution. Now, when I make this thing random, then it does not have any unique ground state. This is important to know. No unique ground state. That means it does not undergo a ferromagnetic transition. Then what does it happen? But it has a properties, macroscopic properties, dynamics becomes slow. Then people computed what are the kind of energy it can have. Well, it doesn't have a unique ground state. So no say E equal to 0 state. However, it has many minima. So now there are all these multiple minima. So if I now plot the energy, again spin configuration, and you have a 3-dimensional system, spin configuration and multi-dimensional. That means spin configuration means I give you very detailed spin 1 up, spin 10 down, all of them I give, and one of them to such a combination, one combination gives you one point in this space spin configuration. So it is a symbolic picture. But the main thing is if I vary the spins up and down configuration, then it has up and down, up and down. People have computed that. So there is no unique ground state, but certain structure and symmetry there. And that turned out to be very important role. So what physicists did, Sherrington, Kirkpatrick, later Derrida and all these famous people, Giorgio Parisi, they said, let me now define, I cannot define unique, but let me define a density of the minima, rho e. Now we find out that we do not always need to, rho e has a very unique character, but the average density has a very important character like a free energy, and we will see that later in this talk. Now look at that, this is minima, multiple minima, it also has barriers. So this is something we talked in our first seminar, which is we call rugged energy landscape. So what then is the energy landscape? Again coming back. First thing to know that what is our x-axis is a multi-dimension. Actually along the x-axis I have many configurations. Like in this room I can say, okay, the energy of the room is just particular the way you are sitting now. Let us now say that pairwise interaction between the two are different, and I rearrange you. So there is one more configuration. For that I get one more energy. Okay. So the configuration is the multidimensional A of arrangement. So that's why it is x1, x2, x3, x3. But I have an energy that is that. It is not easily, but I gave you an example with it. Now, many times details are not important, but certain significant coordinates I can now group together. I can group together these things certain ways, and I can evolve a significant coordinate that we will do now. Now, some of these are called order parameters. The significant coordinate, which is the combination of my coordinates, can be called the order parameters. Very important term in phase transition, like magnetization, density, local packing. These are my order parameters. Why density is a collective quantity? Because let me tell you, because I had a lot of discussion with two of you today. What is the collective variable? So I told you that today will be a little bit more pedagogical, though we will talk of very important things. If I want to have a density at this n real space, 3-dimensional real space, n particle, then this is a 3n dimension. Then that is defined as all the I particles, that would be the density. Okay. So, instantaneous density, this delta function means that I go to a position r, and if there is one particle there, then that is 1. Then I normalized it. So, what I am trying to tell, and probably not doing a very good job, but try to understand, I am defining a property, and then I can define a property that it is a single particle level density, 2 particle level density. If I average over the density, I get the number density. Okay. So, collective properties are always defined like that, density, or if I want to have a current term essential to our hydrodynamics, then I will do this term. Okay. These are become magnetization, sum over all the dipole moment is the magnetization. Okay. Things like that, then I will average of it if I want to connect to experimental quantities. Okay. Now, this is something all of you must know, which is that what is Landau free energy surface. Landau in 1937, you know, he got a Nobel Prize, he could have probably given 4 or 3 Nobel Prizes. He wanted to develop a very, he observed one thing, that all matter, inevitable of it, undergoes melting, and with a similar characteristics, fractional density, density increases or decreases, water decreases, everywhere increases, then there is a latent heat, there is a discontinuity. But there is a grand universality in the phase transition. There must be a very simple description, and of course it requires a genius to find out a simplest possible, you call the simplicity of the genius, and this is an example of the simplicity of genius. Landau say, okay, I will write down the free energy now, such that free energy of the new phase, this is the free energy of the new phase in terms of the properties of the old phase. So, these are all derivatives, and eta is the order parameter like density or magnetization. These coefficients are all temperature dependent, this is a little bit more. So, these are nothing but a functional Taylor expansion. That means I am expanding free energy of the new phase in terms of free energy of the old phase. Okay. A, B, C, D, there will some of them we need, some we do not need. Okay. Now, free energy, if for 2 phases to coexist, free energy must be minimum. So, this has to be a minimum, this has to be minimum, we will see how it goes, that gives me an additional condition. So, without going into detail, I will tell you how the free energy surface looks. This, as I said, can be density, say gas liquid transition, this is density, magnetic ferromagnetic transition, it is magnetization. Now, first order phase transitions are characterized by similar, this is the free energy landscape. I will use energy and free energy interchangeably, and I will make it quantitative later. So, say this is my gas phase, and I have chosen 0, I have taken out the average, the density of the gas phase. Now, as I lower temperature, this minima, which is liquid phase minima, remember the minima always lurking there, then minima comes down, then this is the coexistence. Now, lower further, the liquid becomes more, I can have it liquid and crystal or anything that you want, okay. A completely universal description, but the important thing is that this minima exists, that minima always here, this is more stable phase, but this is called metastable phase, that always exists, and there is a sizable barrier. Because of the sizable barrier, you need to have a nucleation, otherwise first order phase transition can never take place. Second, first order phase transition show hysteresis. Why? Because this second minima is always lurking there. Okay. How do it for second order phase transition? This is absolute beauty. He said, okay, in first order phase transition, there is no symmetry here, no question of symmetry breaking or things like that. Here, however, in second order phase transition, what happened? Just liquid in magnetization. So, here near the critical temperature, up and down you have a symmetry, and that symmetry must be reflected. So, eta going to minus eta, going to minus eta, it does not It does not, remember my magnetization is eta, okay, this is same as eta. Okay. So, my this term cannot be there, cubic term cannot be there, eta minus eta is not the same, then all odd terms will disappear, my even terms will remain, and I already showed the first term has to be in there. So, now I have a beautiful simple, if I neglect that, this is called what field theory is a phi-4 theory. Now, how does phase transition happen now? It happens, this is the your free energy surface, free energy against order parameter, this becomes flat, that gives you critical opalescence, all the fluctuations at the critical point, but as you go below there is a symmetry breaking now. It suddenly now two phases appear, which are these two phases. So, this beautiful simple, that this explain many other things that I am not going to go, discontinuity, specific heat, then I can expand the Ginsburg-Landau, which is the all your theories of phase transition, whether you do superconduct, superfluidity or all these things, they all come out from this kind of a description. Essentially at the core, this is the free energy which explains all of the phase transition in this world. I have described quite a bit in this book because I love Landau theory. I learned a lot from Landau theory. People these days often ask me, because I work on many different things going from physics to material science, biology, chemistry, and they are all pretty good papers. At this stage I do not need to flatter myself, but they are in good journals and well cited. One of the reasons that few things are very important to a theoretician, and one of them is Landau theory and this picture and the collective thing, and you cannot get better than that. Now I want to understand the landscape further. I said, okay, how do I describe dynamics from the landscape? And this is something which Rajyoshi and people do, that we now have a order parameter says that my configuration coordinate. So this now, this thing and this thing become, these barriers, they become like, suddenly it becoming like isomerization coordinate. I undergo cis-trans isomerization, the angle theta, or I undergo electron transfer, which is called Marcus solvation coordinate, which is the collective coordinate, by the way. Most of the people do not understand Marcus theory. I have another book, I will tell you where we explained it reasonable way. So, in this case, this is the barrier frequency and these are the well frequency, product frequency. If they are the same, then this is the frequency of the well, harmonic frequency, assumed to be harmonic. That means energy varies half omega square x square. Here energy decreases as half minus half omega b square x square, and this is the activation energy from going from here to there. Then we have all these beautiful things that have been done. Actually these are the things which taken over, like this is a transition state theory. This is the one which is done to do nucleation. I am trying to get you the universality of a theoretical description and the similarity that one goes. Actually the Arrhenius theory in terms of the bistable potential, 2 minima, 1 maxima, those things were done, came from physical chemistry. I always say Arrhenius theory is one of the gift of physical chemistry to natural science. Okay. So remember this is omega r and this is, I said this is omega r, but they are more complex. If there is viscosity effect, then this friction is proportional to viscosity. Then you have a little bit more complicated thing, Kramer's theory, if viscosity is large, you have these kind of things. So these various expression of reaction rate now becomes useful in the energy landscape and extremely used in protein folding. Exactly these expressions have been used and combined with energy landscape, which we will go do now. So as I said, these are the things, many of these things which is I shouted at all Rajyoshi students today to not to read this book, because it's a very simple book which describes many of these things. Okay. Now, what are the tools now of energy landscape? Now these I do not have any, so I have to do it here on the board. So let me consider a trajectory. I have a system, maybe a water molecules or anything, sodium, liquid sodium, melt, ethanol, whatever you want. Now let us see, I am following in time the trajectory of the system. So the trajectory means this with time this molecule is rotating, moving, this is rotating and moving, all these things are happening. The dance of molecules, very common language, this is dance of molecules that is taking place here. Now what I do, at selecting intervals, I remove all the kinetic energy. I remove all the kinetic energy. Then what I get, and I do it such a way that I get the local minima. That means I slowly do it, I do it carefully, so that I don't go from cross a barrier. If I do that, then this one will be, say these two, one minimum. So this one will come here, this one will come here. Then by that time it might have crossed over another thing, another minimum. So again flow of the, so by that way, by going through trajectory, so it's a computational. So it's a computational technique, but very common and very easy. That you follow the trajectory, then you find out the underlying minima. These are called basins, and then you get a landscape like that. This is the way, you simplest possible way you get a landscape, and that's what people essentially have in mind. Okay. So once you get the landscape, as I already told you, and I showed you in case of Sherrington-Kirkpatrick model, I have this energy. So let me say this is different a little, then this is here. So I can now say what is the number of minima between E and E plus dE, and this I said my density, essentially my density of minima or density of states or density of relevant states. Then the idea is that I want to describe properties of this, which is at temperature T. I want to describe properties of matter, liquid, solid at this A, but I want to describe in terms of this structure. The hypothesis then is that the underlying minima determine properties here. Okay. How far of this is true? Now we will show you something. So you all know Raoult's law, that classical physical chemistry, that any property is mole fraction P1 plus mole P1 and P2 properties of mixture A and B, and then there is a, we know is a non-ideality. In your Glaston, Castellan, Moore or Atkins, there is no other explanation other than giving the anomaly. Now we simulated two kinds of things. The things that you heard in, read in this undergraduate text, we call them structure former. When A and B like each other, in a binary mixture, two components A and B, when A and B like each other, we call it structure former. When the A and B dislike each other, interaction is less, this is called structure breaker. We have many solid solvent systems which are structure maker, we have many which are structure breaker. Okay. Now is a structure breaker. Structure breaker viscosity decreases as you lower the, as you increase the solid mole fraction. But this is a very difficult behavior to explain for a complex system. So you can do very sophisticated calculation, we have done. But if you look at the average inherent energy, you see that the structure breaking property is very clearly manifested here, almost image of each other, that the average energy goes up. That means the system becomes unstable. They are still mixed, you know, they are not phase separated. I will show you some phase separation here. But this is a beautiful explanation how structure breaker properties reflected in average inherent structure energy. So these are my inherent structures, these minima are my inherent structures, a very common term, I will use it again and again, and then I have taken average over them, average over rho E, and I calculate the average inherent structure energy. Now this is what structure maker does. In structure maker viscosity, you know, we have seen many of these graphs, you know. Few days ago I got, there is an Indian journal which is coming out, which is, just send me there all the papers, actually not any Indian journal, Proceedings of Indian Academy of Science, sorry, Indian National Science Academy, and there are many papers still now from India coming out which are doing the non-ideality of binary mixture. But look at here, how beautiful this is, viscosity goes up, we all know that in structure maker, look at the average inherent structure energy, you know, it just beautifully explains the structure making and structure breaking in terms of energy. Okay. It does huge amount of things in supercooled liquid, liquid crystal. I will have a little bit to talk about liquid crystal. Now I do supercooled liquid little bit. There is amazing beauty that comes into it. So this is the volume or enthalpy against temperature. Now let us say this is let me say this is entropy. So, entropy of the liquid decreasing. This is where it should have undergone a liquid crystallization, melting point Tm. I avoid it by slowly cooling, and some liquids are can easily be made into supercooled liquid. Then I extend it. Then one finds that somewhat below temperature there is a break. It becomes similar to crystal, and there are a lot of very anomalous properties that happens. One magical rule nobody has been able to explain is that glass transition temperature is 2/3 of the melting temperature. For a huge number of people, nobody has been able to explain that. Now, this is called angel plot, very famous plot. Look at the number of things I am plotting: xylene, fluorotoluene, chlorobenzene. Chlorobenzene is a thing that we theoreticians like because very simplicity. Orthoterphenyl, then all these, silicon dioxide, GO2, and I plot the logarithmic of viscosity or relaxation time against 1/T. I have done Tg by T so that this is 1. Look at, for chlorobenzene, orthoterphenyl, this kind of beautiful way. That means in the beginning it's slowly, viscosity is slowly increasing, then it zips, and this is where the glass transition takes place when this becomes very large. People are introduced that some glasses are fragile, which shows this kind of behavior. Some glasses doesn't show, like germanium oxide, silicon dioxide, which is your glass in a window, they show this kind of behavior. It is very important because this gives rise to the strength of glasses. Strength of glass is very important, and a lot of people are interested in it, a lot of industry money comes into it because to understand this temperature dependence of glasses. There are a lot of many beautiful things of relaxation, Debye type relaxation, non-Debye relaxation, as I was telling you, highly non-exponential. Then you have the step, the logarithmic plot, step kind of relaxation, but I am not going to go too much into that. And there is bifurcation. Now, one thing that I want to tell you that many of these things show decoupling from the conventional hydrodynamics. This is the kind of picture we have, the inherent structure. Now, I will show you, this is a very famous Nature paper, but I do not think I have all these slides. So, I have to again do some board work and tell you something amazing thing that happens. So, I plotting the average inherent structure energy. These are kind of 1000 times cited papers. I now plot against temperature, not 1/temperature, temperature. Average, then the beautiful thing that happens, it remains almost invariant of temperature. Then it starts falling. And when it starts falling, this region we call the crossover temperature. Below that, it is non-exponential. And here relaxation is exponential. So, this temperature dependence of average energy is, so this is what I was telling, that I have all the energy landscape, I have different energies, but depending on temperature I explore. Low temperature, it gets stuck here, it does not go there, okay. But high temperature, it goes here and here, everywhere. High temperature, it explores everything, all landscape. Low temperature, it favors the minima, deep minima. There is a crossover in the dynamical property when I go from at low temperature. This was not known before. And then one finds, there are many things that people did not explain before: translation, rotation, coupling, because the molecule is translating and rotating, and there is a coupling and decoupling between them. They decouple, translation becomes faster, rotation becomes slow. All these things are related to this particular temperature, this temperature here, the decoupling temperature. And there is lots of theories that we have worked on, and there is the last, I am talking today only of this particular one, which is the energy landscape paradigm. The Stillinger-Weber started in 1984, but this famous Nature paper that I, this seems like these people published only in Nature. So, this is then is the average energy and the temperature will have this kind of break from high temperature and low temperature behavior. and this is connected to non-exponential relaxation set scene, structural relaxation time to longer, follow Arrhenius no longer follow Arrhenius temperature dependence below this onset temperature. So we were trying to understand that nobody did rotation. So all the people are doing physicists always doing and almost always do translation. So we said, let me do some rotation. So what I do, I took some ellipsoid molecules, we took this, some ellipsoidal molecules, and then ellipsoid has the orientation, and there is a orientation dependent interaction. There is a very famous model called Biman model, which is here, and then that model is a product of rotation and translation. So if hydrodynamics works out correct, then this probably some of you know, the diffusion is equal to kBt by say 6 pi eta r. Eta is the radius. Rotation on the other hand, I am ignoring the mass and moment of inertia. D has 1 over viscosity dependence, so diffusion becomes slow as you lower the temperature when viscosity increases. Rotation relaxation time that you can get infrared study, Raman's study, or you can get from dielectric relaxation, you can get from NMR, most important you get from NMR, you can get this quantity. So D against tau, if you made the product, that is independent of viscosity and independent of temperature, because these things cancel, this cancels, okay. It just becomes a property of R square. Does that remain okay? No. You see now that as I lower the temperature, there is a dramatic breakdown in my system of ellipsoidal molecules. This is called translation rotation decoupling, very famous thing. Those days when you were published, I think this was the time we started working on landscape. Just everything was a PRL. Referees never commented on anything, just one I got even just the facts that is going to print. So, but the beauty is that you look at here, it's completely hydrodynamics hold. In this region, what high temperature, where this region. So what we now do, we correlate this region with this region. Okay, and some beautiful things appear in when I go below in this region, in the low temperature region, what I call glassy liquid or viscous liquid. Nature of diffusion, both rotation translation changes. Now we get all these large jumps, and you can say now we can explain from little more detailed theory why the decoupling takes place. Now this is beautiful actually. See, average inherent structure energy, this is the one I plotted here against temperature. This is our own calculations, I think from the same model, ellipsoids model. Their energy is around 1, this beautiful fall in average inherent structure energy. Remember, average inherent structure energy, this thing is invariant. This is the property of the system, it is the property of the Hamiltonian. This does not depend on temperature, but how you explode the landscape depends on temperature. So all the beautiful temperature dependent properties that we see in nature are manifestation. I can explain, I can articulate in the following fashion, is the exploration of the inherent energy landscape. So inherent energy landscape temperature independent, but its exploration, manner of exploration is temperature dependent, which is shown here. Then breakdown of D by rotational dynamics diffusion again, exactly same way. These tau 1 and tau 2 are 2 relaxation times, people all do, okay. So now there are a lot of, another breakdown, several different properties we could explain by doing that. Now I will do something which is really very interesting. This is spinodal decomposition. What is a spinodal decomposition? Spinodal decomposition is this phenomena. I start with a mixture like this, and then I parent liquid high temperature, then I suddenly lower the temperature. High temperature, this region is completely homogeneous, this is a structure breaking system. But look, the inherent structure is phase separated. So high temperature binary mixture that we see, which is this one, Underlying that remains this spinodal decomposition, this stripe. So, if you take out all the temperature, then they will be beautiful spinal, it's like zebra. Spinal decomposition is a very general phenomena in metallurgy, where you see it in rocks, volcanic rocks, the stripes, in the red, if they have ferrous oxide, a lot of them red, then grey, red, very regular stripes they form, and that is a great theory of that by Kahn and Hillard, but this is where we are seeing it at the spinodal decomposition level. And then you can look into some very nice thing, you look into okay, distribution of inorganic structure energy, and you can say where the spinodal decomposition takes place, phase separation by spinodal decomposition, phase separation by nucleation, all these beautiful things you can do. Okay, and there is one more, starting from temporal evolution, starting from A and B, they slightly dislike each other, and then we suddenly lower the temperature and we see the evolution with temperature, then fully phase separated. See, because this is a periodic box, this we are doing a simulation, so these and these are the same, so they are completely phase separated, but they go through a beautiful zebra pattern or pattern, this is called the spinodal decomposition. The Ostwald step rule, anybody knows what is Ostwald step rule? I have talked enough, now let somebody gives the answer. What is Ostwald step rule? A few years ago there was a lot of discussion. Who is the most important physical chemist particularly with the old era? Who got the first Nobel Prize in chemistry? Van 't Hoff. Second, Arrhenius. Third, okay, but these three musketeers of physical chemistry, Arrhenius, Van 't Hoff and Ostwald. Ostwald got little later because Arrhenius, the politics was always there. Arrhenius opposed his Nobel Prize. So, but Ostwald formulated many beautiful things. One of them is that, which is now become very popular in nano synthesis, is that when you suddenly cool something or make an unstable condition, what is the phase that forms? The formation of a phase is not determined by the absolute stability, that is called thermodynamic criteria, but by the closeness of the growing phase to the parent phase. This is called Ostwald's step rule. Nucleation Ostwald step rule is a very famous thing. Now, Ostwald offered no explanation. He just stated that. There are some people who objected. Then Ostwald's these famous lines. What is the confidence that guy had? There are undoubtedly examples of phase transformations where a metastable phase exists but does not form. In such cases, we can always assume that the intermediate structure does form, but then immediately transforms into another phases. This is name of these are vanishing polymorphs, very common in X-ray crystallography. So, and everybody universally accepts this. It's a beautiful line, and then we are going to do a little bit in terms of energy landscape. We are going to give you a little explanation of that. So, 30 years ago by Alexander McTighe argued that metastable liquid phase fluctuations with the local symmetry, they said even those crystals which go to FCC always start at FCC as BCC. That because remember argon goes to FCC, say argon goes at density, okay, FCC density is 0.74, crystal close packed, BCC 0.68, right, and liquid maybe when it is forming it has a packing fraction of about 0.5 or 0.55, but BCC comes before FCC. So, the liquid first form an embryo BCC, then it goes to FCC, and he was many things they have done which were criticized, and so now another phenomena which is people still fighting, pure water, really pure water does not freeze at 0 degree centigrade, that water freezes at 0 degrees Celsius never happens in ultra pure water. It remains liquid till minus 40 degrees centigrade, but this undergoes an explosive crystallization. Why? We already have seen Landau theory that these two phases are separated. So one has to be new, even though this is more stable, it does not happen because this has to be nucleated inside. I will talk a little bit of nucleation. I have gone back to my order parameter, which can be density or order, and this is my free energy. Little bit of nucleation. If you guys have not done it, then that your education is incomplete, whether you are doing quantum chemistry or statistical mechanics. If you do not know the basic theory of Becker-Doring, you know, is a little bit dicey, because this should be taught in the high school. How much energy it takes to create a, I do not need these anymore, so I can. Nucleation you must know if you are a chemist. Inorganic, organic, physical chemist does not matter. So, I am going to now, in a system of homogeneous, I am going to nucleate a different phase, okay. This is embryo or a nucleus. How do I do that? Okay, I already showed you that the free energy landscape is like that. This is the new phase going to form, which is more stable, but it is not forming. This is the old phase, and a free energy difference between this and this is delta G. Then if I want to create an embryo of radius r, then that is the energetics. I have to pay a penalty for surface tension, that is the essence of nucleation, but I gain by 4 pi by 3 r cube, 4 pi r square gamma, this is thing. Then I minimize it, I get that is very famous thing, r square 2 gamma by delta GV, then delta G star, this is a thing. These are very well known expressions of radius of critical nucleus, free energy barrier of critical nucleus. Note here, gamma is surface tension. Note the huge influence of surface tension in the free energy barrier. We did some simulation and we found very interesting thing. From liquid, if we study very difficult calculations of finding the free energy, this is a contour. When they circle like that, that is a minima. Then when it becomes like that, that is a maxima. This is the saddle. We start from here, we always go to VCC. We never went to FCC. It always goes, I envisages, it must be something like that, then it goes like that. But we never find that. However, if you have BCC, one finds a way to go to FCC. This is a very funny order parameter, orientation order parameter, that two order parameter plane. But it otherwise clear. Then you melt the BCC, I will show you that. Yeah, within BCC, FCC grows. Okay, I can show you some more now. Most common example, of course, you know, is zeolites. Okay, this is one of them, faugasite, one calcimite, all the finally quartz. And this is, we start with gel, aluminosilicate. And then there is, this paper came recently in Nature Physics, and several other came where they did the phosphate system. They found all the intermediate phases, starting from here, it goes to final here, but all the intermediate symmetries they find. And amorphous lithium ferrous phosphate transform into a stable crystal via intermediate many crystalline phases, which because of electron microscope now, they can capture these things. Okay. At the same time, a peculiar theory came from spin glass people, Philin, and then Peter Wallines and others, saying that, you know, you have to be a bit careful when you talk of surface tension of small, nucleation of small thing, because surface tension itself can depend on the size of the nucleus. Now, I always give, I give even in all the big lectures, I give this little slide which is in my textbook, how you understand surface tension. Most of us do not understand surface tension. We say, okay, energy required to increase the surface by unit area, right? That is the surface tension. Energy required to increase surface area, they have to be in coexistence. They have to be coexistence means they have to be some free energy, right? The reason is that when you go from one phase to other phase, you have to go through a region where the comfort of, enthalpic comfort of order and entropic comfort of disorder does not exist. So you go to a region where in an order parameter, this is an order parameter, things are not dicey, things are not comfortable. So free energy goes up. But to create a surface, I had to go through this, right? Like you have to get married, you have to put that dabba in your head in Bengali marriage. So that is the reason of the surface tension. So I gave this talk in a very famous university, Rome, Sapiens, forgot the name, and all the physics students were so happy. They came and told me, we understood surface tension. Okay, now, so this is what you are doing, that how your eyes goes to the one conjecture of low density liquid, and how that happens in minus 40 degrees centigrade, that these are the minima, it goes from here to here, it follows here and then kind of gets energy from there and goes to a. Okay, I can consider the following thing. I have a melt, now I am going to Ostwald. I have a melt, I have a stable solid, and I have a metastable solid. What will be the influence of that? We don't know that. Metastable solid might be lurking there. What we are going to show you, that has a tremendous influence on surface tension. It can be also like that. Then melt, metastable solid. These are free energy surface, not the surface tension. Well, there is a very sophisticated theory called density functional theory, which is same as Landau. This is Landau free energy surface. And we are writing in grand canonical ensemble. And this extra term is called Ginzburg-Landau. This Ginzburg-Landau free energy surface. This is a thing of beauty. Then we can calculate. Now we show you one result, this beautiful result. If I have a metastable phase and I am making the metastable phase more and more stable, bringing it down, surface tension decreases. So surface tension between this and that, you don't know. But the presence of a metastable state, surface tension decreases substantially. This is what actually Villein says in his spin glass model, Wallin Zia, Kirkpatrick, Thirumalai said, but nobody really understood this is Wallin's first right. He was absolutely happy that how you go from once to waiting of a phase to Ostwald step rule by varying this thing. And so it is like this. First the metastable forms, let's say metastable 1, then metastable 1 will form first, because this is Ostwald step rule and because of surface tension, these nucleates first. Then within that, these nucleates. Then within that, these nucleates. This is the essence of the Ostwald step rule of 100 years old. But this is here, I think, made really very, and this is what people have seen. Core shell model, many other cases of this. One very big paper will come out tomorrow or day after tomorrow, just did the galley in where all these phosphate and all these things have done. So, supersaturation dependent Habermas nucleation crossover from waiting to Ostwald step rule, role of surface tension, interesting connection with Marcus theory that I am not going to go it. There is amazing, this energy landscape is Marcus theory, just helps us out. So, with last 2 minutes, we did work on insulin hexamer, and that made into big ways CNN news. What we did was very simple. We are doing some experiments with some people in our MBU, Professor Gopal, my good friend, younger colleague. And I told him that, there are a lot of nice things to be done in insulin. I don't know why I got interested in insulin, but I got very interested in insulin. I still don't have diabetes, might have in the future, but so when I started doing it, insulin hexamer, see, biologically active body, now in your body, the insulins are very active, breaking down all the food that you are eating, all the glucose and sugar into carbon monoxide and water and all this energy. Now, however, the biologically active insulin is a monomer. Dimer has some biological activity, not too much, but hexamer is basically storehouse of insulin. When insulin in your body goes down, then this breaks into dimer, then dimer breaks into monomer. That is the biological pathway. So, body stores insulin in a hexamer. There are 2 zinc, there can be calcium here and some water molecules. This creates a cavity, pretty big cavity. So, as a chemist, I immediately thought, what is holding this cavity? Okay, and we did lot of experiments. They did, Gopal and myself, we did simulations. There is a C3 axis, there is a cavity, and then we found there are 10 water molecules inside the cavity. They are all different, hydrophobic force, hydrogen bond. So, what is the role of water? Stability of insulin hexamer. And so, there I think, okay, just I want to show you one movie. These are water coming inside and going out of the insulin cavity and all time correlation functions. So, this is the, if I remove the water molecules, this should be a movie here which is not, so they would have shown you the collapse as I remove the water molecule. So, role of cavity water stabilization of insulin hexamer. Cavity water molecules are slow, they indicate, but it was really fun to figure out what kind of hydrogen bond network they form with histidine. Histidines are bound to zinc, but they are a glutamate there, and so all the hydrogen bond network, how this beautiful architecture of hexamer is. So this is the last piece that we worked out, and I told you that I will show you at the end the huge computational advance and the free energy landscape that we can find now. So insulin dimer dissociation is a important biological process. That how does it? So one does a very sophisticated metadynamics calculation and then pull them apart. So this is the number of contacts between two monomers when they form dimer and the monomer distance. So this is the landscape now. What is the path it follows? This is the deep minima when they are together, and when you go out there is a metastable minima where it gets trapped, but otherwise it has to follow this pathway and then it is fully separated. And that is what I was saying, and we can find the binding energy which is reasonably good with available estimates, and then the minimum free energy pathway we can form, we can find the rate. So this is the level of energy landscape or free energy landscape that has gone now, which was not when we started, we never envisaged that we will have this kind of beautiful free energy diagrams. Then these are all the now one dimensional, the ones that we used to do before, our old transition state theory, okay, and the different states that formed during the phase separation. And then what happened in grains of ethanol, that we started, and ethanol lowered the, even a 5% water ethanol binary mixture shifts the minima to a great, because ethanol molecules come in between, and so it goes from here where contact is about 50, 55 and separation is about 2 nanometer, that goes to contact is much less because insulin has come in between, and this is the pathway. Barrier goes down significantly. So not only free energy barrier decreases, but pathway changes and become less rugged in presence of ethanol. So summary, the energy landscape has emerged as a valuable tool. Tool is means to understand collective phenomena. In strongly correlated systems, energy might dictate free energy, although entropy continues to play an important role. Free energy can be calculated by new techniques like metadynamics written on plane. This is a new picture. After that you can see they are enjoying because it was after a good dinner. She did this spinodal decomposition, Shormishta, in structure. Insulin was done by Shomok and Sayantan. They are really very good. Shomok and Sayantan. The girl on the tree didn't do much. Grishma and other people like Doipayon, their picture is not there. Many other people, Shoikot, they are all not Shoikot, but Doipayon is a professor in Birmingham. Ornov is a professor in Pune, and many other people they have done. But right now, this Somok, Sayantan and Pooja and Shormishta are the ones who did that. Thank you for your attention. Absolutely, it's a very good point. So this I hate there. Energy landscape is the ultimate quantity. Now you can map one energy landscape to another energy landscape to a great extent by changing the tuning the temperature. That is the reason of the universality in the glass transition. That all things behave similarly. That's why so many people working on physics and chemistry, like Europe, gone crazy on this. That is of this universality, and all the, it's a beautiful thing. And energy landscape is now given a little bit. Of course, there are many other theories. This is just one of the few. But what I found very useful, that I can use it to do binary mixture. That was really very satisfying to me that I could explain the non-ideality in terms of inerent structure. Then the liquid crystals, I did not show the, but liquid crystal, there is a beautiful thing, if I can open that up. This is actually a good movie, To Catch a Thief by Cary Grant. Watch that, that's a great movie, but not here. This is not the, if I start playing Catch a Thief, all of you will stay here. Okay. Okay, this is in liquid crystals. This is a liquid crystal that has a very similar view. So, what will happen? Yeah, so what I am saying, isotropic nematic. So, this is the isotropic. Through that, it goes to nematic phase, exactly like liquid thing, the liquid glass transition behavior. And most interesting thing is that in the inerent structure, if there is a smectic in an inerent structure, you do not get nematic at all. Nematic is not the ground state. That is why it made PNS. It was beautiful. And then there are many other similar to, so we compared with the glass transition and all these things. There actually 3 PRL just in those days were good days. But beautiful thing is that is a really you can have it very nice way, you know, it's a very satisfying paradigm because it is when we many times work with radial distribution function, very microscopic details, which are okay and we need that, but sometimes you yearn for a better, more elegant description, which is you can relate to. Energy landscape is such a thing which gives you a certain intellectual pleasure in understanding. Right. Yeah, one of them I just showed you, density for example, or magnetization. Magnetization I sum over all the dipole moments, so it is a collective quantity. Density is a collective quantity. Another thing that we use a lot in liquid, in isotopic nematic, orientational order. Orientational order are spherical harmonics, YLM, maybe moments of, like we do a lot of sum over m y6m, that is called Q6. Similarly with Q4, for water tetraderivative order parameter. That is why I had put in initial, when I said order parameter, I said local quantities. They are local, but they are collective at the same time. I quote Prof. Zwanzig's a great line that, as I am telling Rajoshi and Rajoshi students to read, Zwanzig said, in the hand of an a literate mind, intuition is the most powerful. Read the Zwanzig's 3-page Journal of Statistical Physics, 2.5, amazing. And he said, read, read and read. You know, whether you are experimentalist or a theoretician, the best thing you can do is to read. Nobody is telling you not to talk on your mobile, your girlfriend or boyfriend, but do spend some time on reading. So at the same time you are showing that the icing model. Right. So if I take the exponential of that Hamiltonian and take the log of that, then I get this. Right. Absolutely. Something. Yeah. Taylor expansion is a heuristic thing that so people attempted a great deal to understand the discontinuity that is in phase transition. You know, phase transition specifically diverges. Entropy undergoes discontinuous jump, and there was a great attempt from the day of the exactly doing the kind of thing you were saying, take the e to the power minus beta h, integrate, get the partition function, take log. That was not working, and the reason it was, there is some problem I can tell you, it was solved by Lee, Great Lee and Young, who got Nobel Prize in 1956, but they did it in 1952, they did it for symmetry breaking, parity violation. Now, what Landau did, like being Landau, you know, he said, okay, let me take completely different approach. Let me use symmetry and write down a free energy, he knew very well what he is doing, which is the Taylor expansion. Then let me see what happens. Let me see the symmetry properties, let me see the properties of free energy. And lo and behold, he can explain huge amount of free energy, and without doing your, now if you want to calculate your coefficient A, B, C, D, then you need the partition function or experiment, otherwise you do not need that. Try to appreciate, as I said again and again when I was talking on Landau, the simplicity of genius. This is the out of box thinking, and this is what, you know, genius is distinguished from us ordinary people, and you better appreciate that they are much better than us. Glassy relaxation. Right. But that is in a highly non-exponential situation, that average relaxation time is not that useful, because you may have initially start with say 1 nanosecond, intermediate time you have something like 1 microsecond, at the end you have something like millisecond. Now you have integrate it, get an average relaxation time maybe microsecond. But who cares, because that does not give you a good description, right? Because you have highly non-exponential things cannot be just represented, cannot be represented by one relaxation time. So that is why, so when you go from ordinary liquid, most of the things are exponential. Water is huge example, you know, rotation is 2 picoseconds. People are still working on that. Why water is such a complex liquid, so many hydrogen bonds still a single exponential. There are many theories on that. That same water, when you go below 260 Kelvin, it becomes highly non-exponential. And so, and then people have done it even lower temperature. I can give 2 or 3 talks just on water, because we have a lot of work on water. And one just came out 2-3 months ago, beautiful paper with my collaborators Shinji Saito and Yaomine. And single exponential going to multi-exponential always signal something fundamentally new things or appearing, essentially appearance of what we call correlated dynamics. Dynamics get correlated. I cannot rotate one water molecule without affecting another one. That phenomenon is same in glassy liquids. And mode coupling theory or those kind of things are particularly suitable to describe these non-exponential things, because mode coupling theory allows you to take correlations into account. Energy landscape tells you different view. There is a multiple minima and maxima, and you are jumping back and forth. So there are many rakes. So energy landscape given, these are not at all orthogonal to each other. They are different way, complementary way of looking at the same thing. Yeah, that will be a pleasure. But thank you very much for taking care of. I really enjoyed my stay here. Thank you, and the students.